So the first thing we're going to do with section 2.1 is I'm marking the text activity. And we're going to start in section 2.1, rates of change of limits. It starts on page 55. And you're going to spend about 10 minutes reading through 57. So where you can stop when you get to properties of limits. So as you're reading through these two and a half pages, note the focus here at the underneath the title of the section with some key terms. Kind of take a note of examples and what the subject of the example is, and then take a look at where you can find in the text where it's defining some key terms. So what you're going to prepare with your group are responses to these two questions and filling in these two boxes as well. So I want you to come up with at least maybe 6 terms, and then that you know or have an idea of, maybe 6 terms that you don't know. And then somewhere in the reading, you're going to be able to answer this question: what does a limit do? And somewhere in the reading, you should be able to answer this question: what can a limit be? So I want you to box in the terms you know, circle the terms you don't know, or at least that are unknown to you. Underline the answer to these 2 questions. Underline this question, underline that question. So at this point, you can stop the video and look at those 2 sections in Notability and take care of that activity. And when you start the video up again, I'll kind of go over some really common things that students found. Okay, so I'm assuming now that you've gone through that activity, and in years past what we've found is that these terms are terms that kids kind of have an idea of. They have an idea of what a function is, an output and input. Even some have an idea of what a limit is. They have an idea of what average speed is, the term non-existent, the term theorem, and what it means to approach. Here are some unknown. You notice how limit shows up in both locations. That's okay. Some kids don't know what a limit is, and that's okay. The term epsilon and delta are also terms that have confused kids in years past. In the reading, students were able to find right in that reading where the answer to this question is: what does a limit do? So, and this is a quote from the text: limits give us a language for describing how the outputs of a function behave as the inputs approach some particular value. So let's kind of dissect that. A language for describing how the outputs of a function behave. So the outputs are y values. So it's a language for describing y values and how they behave as the inputs, and the inputs are x values, as the x values approach some particular value. So it's describing your y values as your x values approach a location. So for what can limit be, there were some examples in here. A limit can be a numeric value. It can be a numeric y value, to be specific. And a limit can be undefined. A limit can be infinite. Here's the symbol for infinity. And undefined and infinity are kind of interesting because sometimes they're lumped together and implied to be the same thing, which is okay. We'll talk about situations where that's okay to do as we get into this section and as we get into the course in general. So that's the reading activity. And with this reading activity now, we're ready to kind of jump into 2.1 and take a look at limits in general. And so if you're in class, we'll talk about what technology-free moments are and how we focus on the kinesthetic activity of taking notes. But since you're watching a video, you'll need your technology to continue with the video. The first thing I want to talk about, since it's the beginning of the course, is this screen here. This screen is typically displayed at the end of the hour, but I wanted to come up at the beginning of the class here so I can kind of explain it. So at the end of the hour, after we go through the content, I'll give you a homework assignment. And the homework assignment's listed here. And you typically, the homework assignment's in WebAssign, which is our internet-based homework program. And so you have the option of then doing the homework in WebAssign and getting that all correct. In other words, scoring 100% on that. And WebAssign allows you to have unlimited opportunities to answer the question, gives you the feedback as to whether the question is right or wrong right away. So if it knows if you got the question right, you can move on. If you don't, you can look at your work and figure out where you went wrong. Each section has a proficiency quiz in Blackboard that covers the whole section. So for instance, you can do 2 homework assignments in WebAssign, get them to 100%, or you can do a proficiency quiz in Blackboard, but you have to pass that the very first time you take it. And that quiz is for the whole section, so it would take the place of 2 homework assignments. But like I said, if you don't get a minimal level of proficiency on that quiz, which is either a 3 or a 4 points, then you have to do the homework. The homework is weighted in such a way that you can get 100% without doing all of the questions. So it does allow you to kind of leave a question or 2 unanswered if you're just not understanding every single question. So I'll explain a little bit more as we get to the homework at the end of this unit, or at the end of this lecture. So section 2.1, this is the first day of it, and every day we're going to have an essential question. So for today, the essential question is, how can limits be evaluated and applied? So the first thing you want to do is write that essential question down in your notes. I give you a box at the beginning of your notes to put that down. So you might want to pause the video and write that down, and when you're done writing that down, go ahead and continue with the video. So I'm assuming you've written the essential question down. So let's talk about the definition of a limit as we did, and kind of compare it to what the question we answered, what does a limit do? So it says the function f has a limit as x approaches c. So if we think about that, we have a limit L, that's the output value, the y value, as we approach some x value. And that's really all we need to be concerned
our intuition of what a
about.
Limit even is. Let's review.
That's all we really need to be concerned about, is that the limit is that y value, is that output value as we approach an x value. So the idea of this delta and this epsilon is not so important for us. We're going to look at this definition of the limit here, and we'll get into that with this video here from Khan Academy. So this is kind of getting at what this is saying.
Let's review our intuition of what a limit even is. So let me draw some axes here. So let's say this is my y-axis. So try to draw a vertical line. So that right over there is my y-axis. And then let's say this is my x-axis. I'll focus on the first quadrant, although I don't have to. So let's say this right over here is my x-axis. And then let me draw a function. So let's say my function looks something like that. It could look like anything, but that seems suitable. So this is the function y is equal to f of x. And
So
just for the sake of conceptual understanding,
right
I'm going to say it's not defined at a point. I didn't have to do this. You can find the limit as x approaches the point where the function actually is defined, but it becomes that much more interesting, at least for me, where you start to understand why a limit might be relevant where a function is not defined at some point. So the way I've drawn it, this function is not defined. This function is not defined when x is equal to c. Now, the way that we thought about the limit is, what does f of x approach as x approaches c? So let's think about that a little bit. When x is a reasonable bit lower than c, f of x, for our function that we just drew, is right over here. That's what f of x is going to be equal to. Y is equal to f of x. When x gets a little bit closer, then our f of x is right over there. When x gets even closer, maybe really almost at c but not quite at c, then our f of x is right over here. And the way we see it, we see that our f of x seems to be, as x gets closer and closer to c, as x gets closer and closer to c, it looks like our f of x is getting closer and closer to some value. It's getting closer and closer to some value right over there. I'll even draw it, maybe I'll draw it with a more solid line. And that was actually only the case when x was getting closer to c from the left, from values of x less than c. But what happens as we get closer and closer to c from values of x that are larger than c? Well, when x is over here, f of x is right over here. So that's what f of x is. It's right over there. When x gets a little bit closer to c, our f of x is right over there. When x is just very slightly larger than c, then our f of x is right over there. And you see, once again, it seems to be approaching that same value. And we call that value that f of x seems to be approaching as x approaches c, we call that value L, or the limit. And so the way we would denote it is we would call that the limit. We don't have to call it L all the time, but it's referred to as the limit. And the way that we would kind of write that mathematically is we would say the limit of f of x as x approaches c is equal to L. And this is a fine conceptual understanding of limits, and it really will take you pretty far, and you're ready to progress and start thinking about taking a lot of limits. Let's try to come up with a mathematically rigorous definition for what this statement means. So the statement that the limit of f of x as x approaches c is equal to L. So let's say that this means that you can get f of x as close to L as you want. I'll put that in quotes right over here because it's kind of a little loosey-goosey as how close is that, but as close as you want by getting x sufficiently close to c. So another way of saying this is if you tell me, hey, I want to get my f of x to be within 0.5 of this limit, then you're telling me if this limit is actually true, you should be able to hand me a value around c that if x is within that range, that f of x is definitely going to be as close to L as I desire.
Okay, so that brings us to our definition of our limit here. So again, it's a limit gives us a language. It gives language to describe the outputs as your inputs. So your outputs are your y values, your f of x, your y values. Describes your outputs as your input approaches, your inputs are your x values, some value. And it doesn't matter if you approach it from above or below. And it doesn't matter if we're defined at that location. As long as we're approaching it from above and below and they both approach that same value L, that is the output and that is the limit. So, so a couple things just to note that the x is approaching a value c and this is the output, so the function value. Okay, so we have as x approaches c, the function value approaches or equals some value L. And so just like, just like they were saying in the video, you can get the function as close as you want to L by making x sufficiently close to c. So that's kind of the intent of this picture here, is that as long as we get sufficiently close to c, and that's where the delta comes in. The delta is that sufficiently close to c, then you have a limit value that is sufficiently close to L, and that's where the epsilon comes into play. And don't worry about the deltas and the epsilon, but that is when you see this definition and you'll see it, the deltas refer to that sufficiently close to x, and the epsilons refer to that sufficiently close to the limit value, or the output value. So let's graph this function here. If we graph this function, it looks something like this. Notice, though, when x is equal to 1, this is undefined, and that is right here. This is a hole in the graph, just like in the video. So we don't have a defined value. When x is equal to 1, we get 0 over 0. That's not defined. That's why there's a hole in the graph. Okay? But let's talk about the limit. As we approach 1, so as we approach the value 1 going along this function, the outputs approach this value here. So what is the limit as x approaches 1? Well, the limit is this y value. Remember, the limit is the output value. So as we approach 1 along this function, we are approaching the value 2 on the y-axis, and we do that from both sides. What is the value at 1? It's undefined. We don't have a numeric value if we plug in 1 into this function. That's okay. We can still have a limit as long as we approach that same value from either side. So you have to remember that this limit question and this function value are two different questions, and they don't have to have the same answer. Okay, so let's kind of try to extend that knowledge. Here's the function again, x squared minus 1 over x minus 1. Here's what we were just looking at. The limit equals 2. Okay, as we approach x equals 1, the output value, the function value equals 2, and that is true from both sides. But we don't have a function value here, so the function doesn't exist. So this is our first example. Let's take a look at this next example. The limit is still 2. We're still approaching an output value or a y value of 2 from either side, but now we have this point down here that is defining the value at x equals 1 as the output value 1. So here we have a situation where the function value is 1, but the limit is 2. And here, when we decide to put the dot right in where the hole was, now we have a limit of 2 and a function value of 2. So you can see that in each one of these cases, as we're approaching x equals 1, as we're approaching that location on each one of these functions, the limit's not changing. We're approaching that y value of 2. However, depending upon where this dot is or is not, is going to give us our function value. We have no dot to fill in. We don't have a function value. We have a dot here. The function value is 1. We have a dot here that's filled in. Function value is 2. So if we take a look at the algebraic, this is the kind of the graphical representation up here. If we take a look at the algebraic explanation of both, here's the function, and we know we have a hole at 1 because that's where the denominator is 0. Here's the function, but we've made it into a piecewise, and we've redefined the y value when x equals 1. And here's this function. Notice it looks the same. And we get this function by coming over to this expression, factoring this into x minus 1, x plus 1, and canceling the x minus 1. In other words, we canceled out the denominator. And in canceling out the denominator, we've removed this hole from the graph. We're going to talk more about how to do this, a lot more. That's going to become a really useful strategy for evaluating limits. So let's consider this function, sine of x over x. What happens as x approaches 0? So again, let's take a look at this graph. So when we want to graph this on our graphing calculator, we're going to put in this, and we're going to make sure that our mode is in radian mode. And then let's go from minus 2 pi to plus 2 pi, and let's scale this by pi over 2. Okay, so take a second and then go ahead and hit your graphing window. So take a second and get that set up. Remember to be in radian mode. You might want to pause the video now to get that set up on your graphing calculator, and when you have that set up, go ahead and start the video again and compare it to what comes on the screen. Okay, I'm assuming that that sine of x over x is on your calculator. You're looking at that. Graph with these parameters for the window, and so you should be looking on your calculator. You should be looking at something like that. Okay, so what happens as x approaches 0? X is 0 at this location. So what happens on the left and what happens on the right? Okay, so as we approach 0 from the left and the right, it looks like the graph is approaching 1. Okay, now notice when we put 0 here and 0 here, we get 0 over 0 again. There's actually a little hole in the graph right there. Okay, but our y values, our outputs are approaching 1, so we say that the limit of sine of x over x as x approaches 0 is 1. So let's look at this numerically. Let's take your calculator and hit your table set, and let's start our table at negative 0.3. Let's have our table values go up by 0.1, and let's take a look at your table. So if we look at your table, we notice that negative 0.3, negative 0.2, negative 0.1, as we're approaching x equals 0, from the smaller values, we're getting really close to 1. And as we're approaching x equals 0 from the larger values, again, we're getting really close to 1. So you can scroll down to see more values, but even though we don't have a defined function at 0, we know that we're approaching 1 from either side, so the limit must be 1. Okay, so the value is not defined, but we know the limit. So we say that here's our limit notation we say for this particular function. So we take the limit as x is approaching 0. That's our input value of the function sine of x over x equals 1. That's our output value. So as we approach 0, we're approaching a function value of 1. So that's our limit for sine of x over x. Actually, before we go on into properties, this is going to become a really important limit. We're going to use this limit to find other limits as we re-express functions and we can get sine of x over x ratios and call them 1 as long as we're approaching 0 on the x axis. So our properties of limits is like they follow our properties of numbers. They can be added, subtracted, multiplied by a constant, divided, and raised to a power. So all those things you can do with numbers, you can do with limits. If we have a function f and a function g, and we add them together, their limit is the sum of each individual limit. Or if we subtract them, then their limit is the difference of each individual limit. If we multiply them, then their limit is the product. We can multiply it by a constant, so we can take 3 times a function, and then the limit is 3 times that limit. All that stuff. We can divide them as long as the denominator is not 0. All those numeric properties we have for limits as well. And remember, for a limit to exist, the function must approach the same value from both sides. So let's try this. Let's use the properties of limits to find the following limits. So if we think about this, if we're going to approach 1, we can use this strategy I call the plug-in strategy. So, and this is typically the first strategy we try. And we can do this typically with polynomial expressions. So if I want to find the limit of this function as x approaches 1, I can plug in 1 and see if I get a numerical answer. And in this case, I get an answer of 4, 1 minus 2 plus 5. So if I get a finite answer, then the limit has got to be also that answer. So in other words, if I have a function and it's just a polynomial, it's not a piecewise or anything fancy, and if the y value exists, it also has to be the limit for the function at that location as well. Now let's take a look at this. Can I plug in 3? And so I was going to try it, and sure enough, when I plug in 3, I get a top of 13. So I've got 27 minus 18 plus 4, and I get a bottom of 6. So I get a physical finite value. So the limit of this ratio of this rational function as we approach 3 is 13 over 6. So sometimes we can just plug it in, which is really helpful. Now, for instance, if we're looking at this one, if we would change this to a 1, we'd have a 0 down here. That would be a problem. Okay, but at 3, it's not a problem. For this one, there's no value that would be off limits, no pun intended, but there's nothing that would be problematic about putting a number in here. So this limit we could plug in and find it for any value. So we'll talk a little bit more about when we can do that and when we can't do that. In other words, we're going to talk a little bit more about, does plugging in always work? So let's just talk about what we did on the previous page. If we have a polynomial function and c is any real number, then if we plug in c into the polynomial function and that value is real, that value is finite, that is the limit. And that is also the case for if we have a ratio, just like we did in those two examples on the previous page. So for a limit to exist, the function must approach the same value from both sides. However, there are cases when the function does not have to equal that value. It's weird, but it's true. Okay. So let's take a look at this example. So let's try plugging in -4 first. So -4 plus 3 is -1 to the 2004. So that's multiplying -1 by -1 2004 times. And so you should be able to look at this and go, well, the power's even. I have an even number of minus signs. Multiplying 1 times 1 times 1 times 1, 2004 times is going to give me 1. So this limit is equal to 1. Okay, let's take a look at this one. Let's try plugging it in here. So here is this function. I'm approaching 2. That's way over here. So as we can see, as I approach 2, I approach a location on this function that has a defined value. And so that defined value has got to be my limit since I have a ratio of polynomials here. So I should be able just to plug it in. And when I plug in 2, I get 2 squared, so I get 4 plus 10 plus 6. That's 20 over 4, which is 5. So if we notice when x is equal to 2, okay, as x approaches 2 from either side, the y value approaches 1, 2, 3, 4, 5. Okay. But let's take a look at this. What happens when we change the limit and we approach -2? So when we approach -2, if we try to plug it in, plugging in -2 here gets me 0. And in fact, plugging in -2 up here also gets me 0. That's a problem. That means I don't have a finite answer. There is no defined value for this function at this location, -2. There was over here. It was all good over here. But here doesn't work. So we need another strategy. And so this next strategy is algebraic. We're going to factor this. And we're going to factor this and try to get this re-expressed so that we don't have a problem with the denominator. So if you notice, you might notice that this top factors into x plus 2, x plus 3. And so that's really helpful because now we have a set of factors on the top and we have the same factor on the bottom, and those are going to cancel. And this is the reason why. This phenomenon is the reason why there's a hole right here. Canceling factors creates holes in graphs. Okay, when the factors don't cancel, then we start to have asymptotes, and we'll talk about that later. But when we have factoring and these factors cancel, that creates this hole. And the way to sidestep the hole is to eliminate that factor from the expression. So we can eliminate that factor, we're left with x plus 3. Now we can take the limit as we approach -2 of this expression. We can plug in -2 and get 1. We can get a finite value. And what that value represents is the fact that as we approach this location from the right, we are approaching a y value of 1. And as we approach it from the left, we are also approaching the same y value of 1. And so this, in fact, is the actual limit at this location where we do not have a defined y value. Okay, so this is a really important strategy because it's going to work for all those situations where when we try to plug it in, we get zeros. And this is going to get us out of that jam. So we've got two strategies we're looking at this page. The plug it in strategy, where we're just finding y values because we have this scenario where the y value exists, and so it is the limit. And then we have the algebraic factor strategy, where we've got to re-express this to eliminate that hole, eliminate that location where the function is not defined. So let's take a look at this one. Tan of x over x as x approaches 0. Okay, well, if we try to plug it in first, tan of 0 is 0. Putting in 0 here gives me 0. 0 over 0 doesn't work. Okay, so we cannot plug it in. We cannot use that strategy. Well, and tan of x isn't factorable. It's not like it's a polynomial. So we can't factor it either. So here comes our third strategy. Let's look at some trigonometric identities. Remember how I told you that sine of x over x, that limit's going to become important? Well, it's going to become important here. So I'm going to use a trigonomic identity that says tan of x is sine over cosine. And so I'm going to make that algebraic substitution. And then I'm going to rearrange. So sine of x over cosine x divided by x is the same as saying sine divided by x times cosine x. And I'm going to split this up. I'm going to look at that as sine of x over x times 1 over cosine x. And I want the limit of that as we approach 0. And the reason why this is really important is because in this expression, sine of x over x times 1 over cosine x, we have this identity here. We know that the sine of x over x as x approaches 0 is 1. So we can call this whole thing 1, and then we're left with evaluating this at 0 and to see if we can plug anything in. So I'm going to split the limits up. This is our limit property. We have a product here, and we can take that product and give it each its own limit notation. We know this is 1. Let's take a look at this. Can we plug in 0 here? Is that okay? And so think about cosine of 0, that's 1. 1 over 1, we can evaluate that. So we've re-expressed this using our trig identities and our sine of x over x limit. And this one is a plug-it-in approach. So we're kind of combining our approaches here. So we've got 1 times 1, which is 1. So this limit, as we approach 0, is a value of 1. Back to the double arrow things. Okay. So we've evaluated some limits. Let me talk about this before I jump into the next thing. We've evaluated a couple of limits. We've shown you 3 strategies. We've shown you the plug-it-in strategy. We've shown you the factor strategy for polynomials, and we've shown you one trigonometric identity to get a sine of x over x pattern to help us evaluate limits. Now we really got to talk about what it means to approach from both sides. Okay, so for instance, we're going back to this example that we started at the beginning of the class with. We have x squared minus 1 over x minus 1. We have no defined value when x is equal to 1, because when we put 1 here and 1 here, we get 0 over 0. So we have to look at this limit from both sides. Okay, and we need this approach when we are looking at a value. We're looking at a location that is on the interior of the domain. In other words, if this were an endpoint, it wouldn't really matter so much. We'd only have to look at one side. But since this is on the inside, we've got to look at both sides. So we're going to do this graphically. As we approach 1 from, notice the notation here, it says x approaches 1 minus. That means as x approaches 1 from the left. So the limit as we approach 1 from the left. That's what this means. Okay, it means we're approaching 1. We're approaching this x value of 1 from smaller values. Okay, from the left-hand side, which are the smaller values of 1. Okay, so as we approach from the smaller values, okay, and then this notation, x approaches 1 plus, this means the limit as we approach 1 from the right, or the other way we could say it, this limit we approach 1 from the larger values. So the plus here indicates that we are approaching 1 from values larger than 1. Okay, so those are the two notations. So that's what we call a double-sided limit, because we're looking at it from the smaller side and then we're looking at it from the larger side. And so just visually, we can see that they both approach a y value, an output value of 2. So remember that calculating limits gives us a language to describe outputs. Outputs are y values. And we're describing this y value as we go along this function. This y value is trending towards 2. So since they both trend towards the same value, 2, then we say that the limit overall, notice there's no plus or minus there, the limit overall as we approach a 1 is the value 2. Notice that we don't have any other defined values at x equals 1, so the function value doesn't exist at all. So the question then is find the limit as we approach 1, and that answer is 0. And that means checking both the limit as we approach 1 from the left, the smaller values, and as we approach 1 from the right, the larger values. And we have to make sure that those values are equal. So one-sided and two-sided limits. So we need that two-sided limit. We also call them right-handed and left-handed limits. Okay, we need that on the interior. So in other words, in order for a limit to exist, we have to have the left limit or the right-hand limit as we approach from larger values, and a left-hand limit. Those have to be the same value, and then we can say the limit exists. And that's when it's on the interior. Okay, if it's on an endpoint, then we only need a one-sided limit. We'll talk about that in a little bit. So so here's, for instance, here's a piecewise function. We have some sort of line that has a slope. It looks like the slope is up 1, right 2. So maybe it looks like a slope of a half. And then we have a location here at x equals 2 where we switch from that line to a horizontal line with slope equals 0. And not only do we switch from one line to the next, but we actually jump down to a defined value here and then back up to that line. So we've got a lot going on here at this location, x equals 2. So if we approach a y value, as we approach x equals 2 from both sides, we're approaching a y value also equal to 2. So that means that the limit as we approach an x value of 2 exists. It's a y value of 2. They just happen to be the same value. But it's not 1. Now the value 1 here is the function value. So the limit is 2, the function value is 1. Here is an example where we have endpoints. So where this example, if I go back here, where this example, this function went on forever and this function went on forever, the domain was infinite. This function, this piecewise function, has a start here and an end here. Okay, so that means we just have to, at the beginning and the end, we just have to look at one-sided limits, and we'll talk about that when we get to them. But let's just start and try to find the limits visually. This is all graphical here. What about the limit as we approach 1? Well, let's look at the left-hand limit. And as we approach 1 from the left, we're approaching 0. And then let's look at the right-hand limit. As we approach an x value of 1 from the right, we're approaching a y value of 1. Our function value is also 1, right? Because this is where the dot is colored in. So the limit does not exist. Okay, we have what we call a jump here in the piecewise function, and we'll get to why it's called a jump in the next coming days. But we do not, since the left hand and the right hand limit are different values, we don't have a limit. Let's look at 2. So as we approach an x value of 2 from the left, from the smaller values, we have a y value of 1. When we approach x equals 2 from the right-hand side, the larger values, we have a limit of 1. Okay, our function value is 2. But since our limits are the same from the right and the left, that means our limit exists. Our limit at 2 is the value 1, because those left-hand and right-hand limits match. Our function value is something else, and that's okay. Let's take a look at 3. As we approach an x value of 3 from the smaller values, we approach a y value of 2. As we approach an x value of 3 from the larger values, that's this arrow, we also approach a y value of 2. So those outputs, or those y values, are the same. And our function value also happens to be 2. When x is equal to 3, our function value is 2. It's because these two are the same that the limit exists, and the limit is 2. Okay, we also have a function value of 2, so everything comes together nicely there. We'll talk about that in the next section as to what that means. Okay, so let's go back to the endpoints now. We've done 1, we've done 2, we've done 3. Now we got to talk about these endpoints. Because we have a defined beginning and end, so in other words, this piecewise function has the domain from 0 to 4. Remember, domains are along the x-axis. We don't need to do two-sided limits at the endpoints. We just need to do one-sided limits. So for instance, we don't care what happens out here for larger values. All we care about is what happens as we approach 4 from the inside, from the interior of this domain. So as we approach 4 from the interior, we are approaching a y value of 1. That's the left-handed limit. The right-hand limit doesn't exist because we don't care about anything to the right of this piecewise function. Our domain is only from 0 to 4. So because we have a left-hand limit, we don't care about that. We have a limit, and the limit is 1. Our function value is also 1. So we have a limit, it's equal to 1, and it's because we just have this left hand defined limit. Let's look at the right hand, the right side. It's a left-handed limit, but it's approaching this end of the piecewise function. I guess I didn't do it. I didn't do this one at x equals 1. So if we did that one, as we approach an x value of 0, we're going to approach a y value of 1. And again, that's going to be the limit there at that endpoint as well. I'm not quite sure why I didn't include that. So what did we accomplish? Well, we accomplished a couple of things. We defined a limit, and we know that limit, taking that limit, that gives us a language to describe our outputs, our y values, as we approach a certain input, or as we approach a certain x value. The pitfalls is that we got to be really careful about plugging in numbers and getting zeros in denominators. So I must not forget to try plugging in numbers first to find limits, but using the other strategies, the factor strategy and the trig strategy, if I get undefined values like 0 over 0. Explaining the difference. What does this notation mean? This notation means function value. It means y value. This notation means taking the limit of a function as we approach a certain x value. And must they be the same? Nope, they don't need to be the same. In fact, this doesn't even need to exist for this to exist. So, so there's kind of a quick summary of section 2.1. At this point here, we're back to the screen now. So at this point, you should be able to do this first day of homework, rates of change and limits of day 1. If you're thinking you want to try the proficiency quiz, remember the proficiency quiz is on the whole section 2.1, and 2.1 has 2 days. So you might want to wait on this until after you do the day 2 lecture. But remember, the only way you can get credit for the proficiency quiz is to score a 3 or a 4. Anything below a 3, and you have to do the homework. So you might want to at least look at the homework and try a few, just to be sure if you're really counting on getting that 3 or 4.